All right, so we're going to cover chapter 5 tonight, and it's on probability. We're not going to cover all of it, it's too much, obviously, but I do want to get started with it. And please do read chapter 5 in the book, although I don't think this is the strongest topic in the book. So I'm going to also go over it to make sure that you guys feel comfortable with everything in chapter 5. So I do have a handout, and let me see something here for a second. And I just realized that I think I put chapter 4 in with my chapter 5 handout. So that's okay. It's not a big deal. It doesn't hurt to have it again. So here, let me share the screen. I believe I already gave you chapter 4. This is supposed to be the chapter 5 handout, but the first couple pages are probably chapter 4. Yeah. So I accidentally included it in the chapter 5 notes. That's okay. It's not a problem. Let me just make sure I got all the chapter. Yeah, there's 8 pages in chapter 5. It can't hurt having chapter 4 again here. And I believe we went over this last time right at the end, right? The sampling methods in chapter 4. And I wanted you to pay attention to the 4 major methods of probability sampling: simple random sampling, stratified sampling, cluster sampling, and systematic sampling. I went over an example for each one, did I not? Did I go over examples for this? Yeah. The simple random sampling really.
I don't remember.
Yeah.
Yeah, me either. Sorry, it's been a weird week.
Oh, okay. So let me just briefly review it again. So probability sampling means we're using some random sampling. We're assigning a probability to each person in the population. Simple random sampling means we're creating a sample. Maybe let's say 100 people out of 1,000 of the population. 100 is going to be our sample size. And what we're going to do is, if we can do it, is, well, let's say number everybody in the population from 1 to 1,000. And then we use some sort of random number generator, and we pick 100 random numbers from 1 to 1,000. And then those people who have that random number assigned to them, they get selected for the sample. And simple random sample, what it really means is that every sample of size 100 would have the same probability of occurring. So your sample that you picked of 100 people would have the same probability as any other sample of 100 that you could possibly pick from that population. On here it says every person or element in the population has an equal chance of being included. Well, that's true for any probability sample. But simple random sampling, and I guess I should probably modify this. Simple random sample means every sample of a certain size has an equal chance of being the sample that you get. Stratified sampling means we divide the population into non-overlapping groups. So everybody's in one group, and we do a simple random sample within each group. So every group is represented in the sample. And so we have group subtotals, in our results, and we have the overall sample results too. Okay. Cluster sampling, we also divide the population in non-overlapping groups, but instead of dividing the population, instead of selecting people from every group, what we do is we take a random sample of the groups themselves. And once we have the random sample of the groups, then we select everyone within each selected group. Systematic sampling means if we have some process which is sort of like an assembly line. You can picture an assembly line where there's some units coming off the assembly line. And let's say we want to check a small fraction of those things that are coming off the assembly line for some defects. So what do? Well, we randomly select a number from 1 to k, so k will be some number. And then every kth unit after that comes off the assembly line is also selected. So the randomization occurs in the very first item that comes off the assembly line, and then everything after that will be systematically the same position that's going to be selected for the sample until we get all the individuals that we want for a sample. That's why it's called systematic sampling. And then there are, of course, the non-probability samples that are not based off of any probability system. Convenience sampling, of course, means that whatever's available to us to sample, we take that. Quota sample, it looks like a stratified sample, except because we have our groups, but we don't do a simple random sample within each of the groups. Right? That's called a quota sample. And then these other two samples are pretty much similar in the sense that there's no probability involved. For example, purposive sample means we choose people because they have some sort of trait that we think is, oh, wait a minute. It says members chosen specific because they are not typical of a population. All right, so you're picking some people who have a specific trait from the population to represent that trait in the population. But of course, the problem with that is that the individuals may be different for other reasons too, and you're not controlling for that. A judgment sample that you may think that the sample that you have is based on that's representative of the population. So there's just some feature that you're picking that says, yes, all these people represent the population. But again, you're not controlling for other possible factors which may influence the results. So all of these 4 non-probability samples can be biased and much different than the population as a whole. That's why we want to avoid doing a non-probability sample. Right? And then, of course, in chapter 4, there's some definitions that you need to know. And you need to know these types of errors that can occur. Sampling error just means that anytime you have a sample, the results are going to be different than the population. All right, and then there's going to be differences from sample to sample too. A response error could be that the people who are responding to the survey or sample may be biased. So there might be some distortion there or bias based on the responses. Non-response bias means that the people who aren't responding may be quite different than the people who do respond. So there's a bias there too. And then, of course, knowing the difference between experiments and observational studies. Right? Knowing that experiments that you're controlling for the variables that affect the response. Observational studies, you're observing those variables. So experiments, if you have a randomized experiment, you can talk about cause and effect. For an observational study, because you're not controlling for other variables, there's no randomization occurring, then the results, you can talk about correlation between variables, but you can't necessarily talk about cause and effect. All right, all that's explained in chapter 4. I hope you do read it. Now, probability. So chapter, let's actually go to this PowerPoint also. But let's actually go through these definitions first and then back to the PowerPoint. Please don't confuse the idea of an experiment in probability terms with the experiment as an actual study. When they talk about an experiment in probability terms, what they're referring to is some sort of procedure that you're doing with a particular outcome. It's something that you're doing or measuring that results in an outcome. For example, flipping a coin, there are two possible outcomes when you flip a coin, heads or tails. One flip, and you flip the coin 10 times and record how many heads that you get in those 10 times. That's a probability experiment. This is something that's systematically done, and you're having trials, just like you do in a regular experiment. But that's what they mean by experiment here. It's something that's repeated over and over again. Sample space refers to all possible outcomes of an experiment. So let me give you an example with the flipping of the coin. A sample space for the flipping of a coin would be heads or tails. There would be two possible outcomes when you flip the coin once. So the sample space would consist of two possible outcomes, heads or tails. If you flip the coin twice, there are four possible outcomes. What are they? Well, both of them could be heads. Both of them could be tails. The first one could be heads and the second one tails, or the first one is tails and the second one is heads. Those four possible outcomes. That's your sample space for flipping the coin twice. If you roll a die, six-sided die, the sample space for rolling it once is there's six possible outcomes. One dot all the way up to six dots. If you roll a die twice, now most people get confused with this. Most people say there's 12 possible outcomes, but there isn't. There's 36 possible outcomes. All right, because if you roll it once, let's say you roll a one on the first one, there's six possible outcomes for the second roll. If you roll a two, there's another six. So 6 times 6 is 36 possible outcomes. So that's what sample space is referring to. An event is some subset of the outcome of the sample space. All right, it's one or more outcomes from that sample space of an experiment. For example, if you roll a die and you say, I want to know I want the event of rolling an even number when I roll a die. Well, the even numbers are 2, 4, and 6. So how many outcomes? That's 3 outcomes of the sample space. All right? Is that clear? Okay. The sample space, by the way, itself could be considered an event, right? The whole sample space. Probability is a number that is dealing with the chance that an event can occur within a sample space. And it's always from 0 to 1. Now this seems obvious, except when in the past, when I've taught statistics in the past, when I ask for probability answers, I many times get answers that are negative or greater than 1. So probability can never be negative and can never be greater than 1. The reason for that is the 0 probability is referring to something that's impossible, right? And probability of 1 means absolutely certain. So I don't know what a negative probability means. Does it mean it's less than impossible or more than impossible? I don't know what that means. And greater than 1, what does that mean? More than certain? Again, I guess people say that, right? It's more than certain, but it doesn't really make any sense. All right, so just remember that the probability is always from 0 to 1. Now, the way we represent in symbolic terms an event, we use a capital letter. The only capital letter I would not use, or capital letters I would not use, is, for example, in many books they use the capital letter S to represent the sample space. Sometimes they may even use the letter U to represent the universal set, which might be the same thing, the sample space. So we try to avoid those two letters, S and U, when we talk about an event. So we can write down a probability event A being between greater than or equal to 0 and less than or equal to 1. So we would say P, and in parentheses, we'd have the symbol for the event. Now, There's a term also in probability called the complement of an event. Notice the word complement is spelled with an E after the L. And you hopefully know that if there's an I after the L for the word complement, it means something that you said, it's something that was, something that was said nice to you. Somebody complimented you and said something nice to you. But the word complement here doesn't mean that. The word complement means it sort of fills in what you are not. For example, you could say, my spouse is the complement, right? Because whatever I don't have, my complement my spouse fills that in. So the way to understand a complement is that we use, first of all, every book's a little different in terms of the notation for complement, but in this book, they use, again, if the event is A, they use an apostrophe next to it to represent not A. So when you see that apostrophe, just say not that event, not that event. So this is a true statement here. The probability of A plus the probability of not A is equal to 1. It's absolutely certain that the probability of A, whatever it might be, plus the probability of it not being A in that sample space, these two probabilities is the same thing as saying the probability of the sample space, which is always equal to 1. Okay? So if the probability of A is 1/4, then the probability of not A must be 3/4. So we can write it like this. The probability of A is equal to 1 minus the probability of its complement, just by simply subtracting the probability of not A from both sides. Or you could also subtract the probability of A from both sides and say the probability of not A is equal to 1 minus the probability of A. These come in handy sometimes when we want to find a probability where there's many different outcomes. Okay? Many times we want to, and let me give you an example. Suppose somebody asks, what's the probability? Let's say we have, let me think of something. Let's say we roll a die. What's the probability of not getting a 1 when we roll a die? Well, you might decide, all right, it's the probability of getting a 2 plus the probability of getting a 3, all the way up to 6, right? But an easier way of doing it is saying it's 1 minus the probability of getting what? Right? So the probability of not getting an A, of not getting a 1, would be 1 minus the probability of getting a 1, which would be 1 minus 1/6, which is 5/6, right? So these equations here come in handy sometimes. It's just time saver many times. There are 3 approaches to probability. Let me just start with number 3 first, because it's the one that most people use. And it's basically the belief that your own belief of what chance an event may happen. Somebody might, you walk out and look at the sky and say, oh, I think the probability that it's going to rain today is 1 out of 10. Right? I haven't heard the weather report, right? But it's clear, and I'm thinking, well, there might be a chance it rains later, but I'm thinking it's a low chance. Well, that's just based on belief. So that's called the subjective approach. And that's what most people use. Now, the classical approach would be for something that it's something that you can guess ahead of time based on randomness, such as flipping a coin, a fair coin. We know the probability of heads is 1/2, probability of tails is 1/2, right? If it's a fair coin. So that's and how do we know that? Because what are the number of possible outcomes in the sample space? There's 2 when you flip a coin. So 2 is in your denominator. And we want to say, what's the probability of getting heads? Well, there's only 1 outcome in that sample space, which is heads. So 1 out of 2 is the answer. This is how we formulate a classical probability. We know the number of possible outcomes in the sample space. That's your denominator, and the number of outcomes of your event. If you know it, that's your numerator, and that's classical approach. All right. So that would be, I mean, we could do something like, you know, you roll a die twice. What's the probability that you get the sum of those two rolls is a 5? Well, we know the denominator is 36, right? 36 possible outcomes when you roll a die twice, right? What's the numerator? Well, the numerator would be all the possible outcomes that add up to 5. That would be 1 and 4, 4 and 1, right? 2 and 3, 3 and 2. There's 4 possible outcomes. So 4 divided by 36 or 1 divided by 9 is the answer. So they can be, the classical approach means we know the sample space and we know the event, and we can count the number of outcomes of both. And we can just plug it in without actually doing an experiment. We know this ahead of time. If we don't know it ahead of time, we do what's called the relative frequency approach. That is, we run an experiment, and the denominator tells us how many trials of that experiment that we run. So if I flip a coin 10 times, 10 is the denominator. And I want to know how many heads that we got. That's the result of the experiment. Or maybe you got 6 rolls, six flips of the coin that were heads. So the answer would be 6 divided by 10. All right. How many heads did you get when you flip the coin 10 times? Now, of course, you can use the classical approach for that, right? And come up with an answer. But if you actually run the experiment, it's the relative frequency approach. This is, again, often used when you don't know, cannot use the classical approach. Surveys. If you ask a question on the survey, right? Let's say you ask the question, are you going to vote for candidate A versus candidate B, right? And you ask 1,000 people. And let's say 450 people say they like candidate A. Well, 1,000 is your denominator because the number of trials is the number of people that you've asked in the survey. And the numerator is 450. That's the number of people who said they like candidate A. So 450 divided by 1,000, or 0.45, is the probability, the estimated probability. Now that's the thing. With a relative frequency approach, you're estimating the probability of the entire population, right? Now, whether it's a good estimate or not is another story, right? It depends on whether it was a random sample and that sort of thing. But this is an approach where you're using relative frequencies, right? Relative frequencies. Remember when we did the histogram, right? And the frequency, right? We did that last time. Did we do that last time? And instead of counting the number of people in each of the classes, we're taking a relative frequency of each of the classes, which means it's the count for that class divided by the total number of people in the survey. So those are the 3 approaches. In statistics in general, we're going to use number 2 most frequently. No pun intended. Most frequently, we're going to use number 2. But you need to know number 1. And the reason why you need to know number 1 is something called, and they don't really talk about it much in this book. Maybe they will later on. It's called the law of large numbers. The law of large numbers says the following. If you increase the number of trials to a very large number, the relative frequency will approach the probability of the actual population. That's called the law of large numbers. That's why insurance works. Insurance works because, let's say life insurance, right? How do they come up with those premiums that they charge you for life insurance? And life insurance, by the way, hopefully you know what it means. It means you pay a premium and then the life insurance company only pays if you die, all right? So how do they know what to charge you? Well, they use probabilities. They know pretty precisely in a macro way how many people are going to die in each age group. Right? And when they know that, they can estimate this probability. And then they use sort of, without getting into much detail, they use some sort of present value calculation. This is a finance type term with interest rates and all of that. And they come up with a present value of what this life insurance policy is worth in the future. And that's your premium. And it requires you to know probability. So probability becomes almost certain. I'm not saying certain. It's never certain. But it becomes almost certain when the number of trials becomes very, very large. All right? When it's very, very large, then the relative frequency probability is very close to the classical probability. For example, if you flip a coin 1,000,000 times and you want to know how many heads you got, no matter how many times you've run that experiment, you're going to get pretty close to 0.5. You're going to get close to it. However, if you flip a coin 20 times, then there's going to be more variation if you run that experiment over and over again. Much more variation in terms of the actual relative frequency probability. But if you run that, if you have many more trials, thousands or millions of trials, then no matter who you are, you're going to get very close to the classical answer of 1/2. All right? And that's called the law of large numbers. All right. Now, another way of talking about chance is what's called the odds. Now, you've heard people sometimes use the term odds when they really mean probability. What are the odds of something happening? They say, oh, it's one, a quarter chance. They really mean probability. And this is a term that's really misused. The only people who actually use it correctly are the gambling sites, the ones who gamble on sports or elections or whatever people gamble on, the casinos. They use odds. Now, there's two types of odds. They don't really go into it very deeply in the book, but they do talk about odds. Odds in favor of something occurring. Let's say we have two events, A or B. Let's say two teams are playing each other, right? We want to know what are the odds that A wins versus B wins. Well, it's calculated by, it's really the probability of A divided by the probability of B. Okay, that's the odds. Okay. Now in the book they said you count the number of outcomes for A and divide it by the number of outcomes for B. But if the denominator for both probabilities are the same, you can. I think it's easier for students to remember this, as long as the denominators are the same sample space, right? It's a probability of A divided by probability of B, because the sample space gets canceled out when you do that. In real life, the odds are actually, when they talk about sports, they're actually talking about odds against. For example, if they say a team has a 1 in 3 chance of winning the Super Bowl, all right, that's odds against. Because the numerator is the probability of the other person winning versus the probability divided by the probability of you winning. Now, it's not really a division here. It's when we do this division here, we're going to have an answer as 1 to 2 or 2 to 1 or something like that as the odds. But that's what it means. Now, let me give you an example. If the probability, actually, a good example would be rolling a die. Let's look at two possibilities. You roll a 2 or you don't roll a 2. If you roll a 2, the probability is 1 out of 6. Probability of not rolling a 2 is 5 out of 6. So you might say, what's the odds of rolling a 2? Well, it's 1 to 5, because The probability of rolling 2 is 1 out of 6. The probability of rolling, not rolling a 2 is 5 over 6. And the 6's cancel, and you end up with 1 to 5. So there's a 1 to 5 odds of rolling a 2. All right. If you want to know what are the odds of against rolling a 2, then it would be 5 to 1. Just the reverse. Okay. And then you do the reverse. If you have odds, you can do the reverse to find the probability. For example, if your odds are 3 to 2, let's say it's 3. Let's say that your odds of winning something is 3 to 2, right? What's your actual probability? Well, the sample space would be 3 plus 2, which is 5. So your probability of winning is 3 out of 5. If the odds against is 3 to 2, then it's the opposite. Your probability of winning is 2 out of 5. All right? Does that make sense? So that's what they talk about that in the book. And I'm not going to spend a whole lot of time on this. This is not a gambling course. But, but the fact that it's used in the world, just know that sometimes people misuse odds and they really mean probability. All right. I'm not going to spend too much time on that. Now, there's certain rules in probability that we're going to go over. And I want to show you the symbols. Now, in the book, they use words instead of these symbols, but I'm going to use some symbols that are used in sets. You probably all studied sets at some time in your math career. One symbol in sets looks like a U here. You see this U here? Sorry. And that can be replaced by the word or. This is the union symbol. So when I say the probability of A with this U and B, I'm really saying A union B or A or B. They mean the same thing. And then the symbol, this symbol here, where it's an upside down U, you can replace that with and that means A and B. Or another word for this symbol is intersect, right? So union means or, intersect means and, okay? So we're going to talk about this, and I'll go through the PowerPoint in a minute, but I want to go through these formulas here. If we look at two events and we want to know what's the probability of one event happening or the other event happening, and the two events are called what are called mutually exclusive. Mutually exclusive means the two events can never occur at the same time. Okay, so you roll a die, right? You roll a die, and you can get a 2, you can get a 3, you can get a 4, whatever. All those events are mutually exclusive. They can't occur at the same time when you roll a die once. You get either one or the other one, right? One of those 6. But you can't get more than one of those at the same time. So they're mutually exclusive. And when events are mutually exclusive and you say or, you simply add up their probabilities. However, if two events are not mutually exclusive, that means they could occur at the same time, then what happens when you add the two events together, you have to subtract the time when they occur together, because the time that they occur together is included in the probability of A, and it's also included in the probability of B. So you're double counting that. And so to make sure that you don't double count it, you subtract one of them. And this is the event that A and B occur together. A intersect B or A and B. So we add the two probabilities and then subtract the double counting. And this is the general law of addition in probability. And we use the word or. Now, multiplication occurs when we use the word and. Okay? And we have two events again, and we say, what's the probability of A and B occurring together, or A intersect B? Well, if the two events are independent, now what's independent mean? subtle difference between this and mutually exclusive. When I say two events are independent, it means that if you have one event and then another event occurs, let's say you have event A, and here comes event B. Event A and event B are independent of one another if the probability of event A does not change with the appearance of event B. So for example, if I think the probability it's going to rain is 1 out of 10, and then another event comes by and a car just passes by. All right, that's event B. Now look outside, I think it's 1 out of 10, and then a car passes by. Do you think the fact that the car passes by changes my probability of it raining? Probably not, right? Like, who cares if the car rides by? It's not going to change my probability of it raining. So in that case, the two events are considered independent of one another. Their respective probabilities do not change based on the fact that the other one is there. Therefore, to say that the probability of A and B occurred together is simply the product of their individual probabilities. However, this is going to get into something that we haven't gone over yet, so I'm going to talk about this in a few minutes. If the two events are not independent, that is, they're dependent on one another. In other words, let's say you look outside and you guess, oh, I think the probability it's going to rain is 1 out of 10. And then you turn on the TV and there's a weather forecast, and they say there's a 40% chance of rain. And then you immediately upgrade your 1 out of 10 to 4 out of 10. Then there's two events there, right? The event of looking outside and the event of turning on the weather forecast are not independent. They're dependent on one another. In other words, the second event is changing the probability of the first event. So the way to write this is the probability of A and B occurring together can be written in one of two ways. It's the probability of A given the event B. So basically, the probability of A now is changed based on B times the probability of B. Or if we were looking at the probability of B given A has occurred, this is B given A, and we multiply it by probability of A. Now, we'll get into this in a few minutes. This is what these symbols here, probability of B given A and the probability of A given B, these are called conditional probabilities. That it's the probability of something occurring given some other event. So the way to read this one here is the probability of A given event B. This one says the probability of B given event A. And it's actually, both of these are ratios. So a conditional probability is A and B together, probability of A and B in the numerator, and then whatever the conditioned event is, in this case it's B or A, is what's in the denominator, the probability of that. So the numerator is the same, but the denominator is the event, the other event that has occurred. So in this case B, in this case A. You see the pattern there? Okay. Now, just for terminology purposes, the probability of A, the probability of the B are called marginal probabilities. You'll see in a minute why they're called that when we look at an example. They're called marginal probabilities. The probability of A and B is called a joint probability. It means the two events occurring at the same time together. Okay. It's called a joint probability. Another way to talk about probability of A and B is also unconditional probability. We can talk about it in that one too. And then we're going to go look at, probably not this time, this will be complicated, but a variation of this idea of a conditional probability is what's called Bayes' theorem. Now, Stephen, you're in the medical PhD in medical field or biological field. Is that true?
Yeah.
So this is used very much in the medical field, but has applications everywhere. And we'll get to that, not today, a little bit later, but this is more advanced. All right, I won't even spend any time on that. Now let's go to the PowerPoint, and just want to make sure that I filled in everything. Okay. Now, in the beginning, the first couple slides here, they're going over the learning objectives, which we'll be covering. Some of the terms that are used. We covered some of them so far. We've already gone over this, right? The probability of a single event goes from 0 to 1. Its complement is 1 minus the probability. I talked about the law of large numbers. Odds versus probability. This is an actual example here. So it says here, if the probability it will rain tomorrow is 20%, and the odds it will rain, then the odds it will rain is 20 to 80, right? Because the denominator would be 100 minus 20, so it's 1 to 4. So that's the odds that it will rain tomorrow. The odds that it will not rain tomorrow is 4 to 1. And then if we have the odds as 3 to 2, this is the example I gave to you before. You just add the 2, 3 and 2 together to give your denominator, and the probability that it will occur is 3 divided by 5. Here's your example of mutually exclusive. We will go into this a little bit in terms of a Venn diagram. You've probably seen these in the past. These are little rectangles that we put circles inside or squares inside to represent events of a sample space, but we're going to show you how that works. And then inside the Venn diagram, you would see these maybe circles that represent events, and sometimes they intersect. Now, we're not going to get into a lot of detail or very complicated cases. We could, but we're not going to do that because we need to really get into statistics. So there's intersections. We could just talk about A and B intersecting. You could picture two circles like these two right here intersecting, and then the space that they share is the intersection. The union of two events, let's say these are the two circles here. Forget about this third circle for a minute. The union of these two circles would be this area plus the area that they share plus this area here would be the union of those two circles. And then if this is the general rule for addition, where where two events do intersect, we subtract off the double counting. And then of course, they mention that if events are mutually exclusive, this here doesn't exist, right? It's 0. Two events are mutually exclusive. Their circles don't intersect. There's no intersection. Then I talked about marginal or simple probabilities, right? Joint. Now, marginal and simple mean the same thing. Probability of A or the probability of B. Joint means there's two events that are occurring at the same time. They sometimes use the word compound, but that's like most of the time they use the word joint. And then we talked about conditional probabilities. Now, conditional probability, if it says probability of A and has the bar B, this is the probability of A, but it's conditional on the fact that B, the event B, is there, and we have knowledge of it. Okay, so this is still the probability of A, but it's conditional on B. And many times these types of probabilities are looked at in terms of a table. You could look at this as a frequency table where we have two different events. One event, in this case here, it would be some location event, such as North America versus South America. Let's say North America is N, and then the complement of N would be South America. So we're talking about the sample space being North America and South America. And then gas wells, right? Some gas wells are dry and some are not dry, okay? So we use dry, we use D for dry, and we use complement of D as not dry. And so we're looking at how many gas wells are we looking at here? Can not any of you say how many gas wells were in this study? I think it was during 1986 in North and South America. What was the total number of gas wells that were looked at? Based on what table that you're looking at there?
48,673.
Thank you. Well, that's exactly right. That's the total. So this is typically your total number in the sample, in the survey, or census. Maybe it's a census, but most likely a survey. How many were in North America?
45,706.
Right. How many were dry?
14,131.
How many total were dry?
14,535.
That's right. So these are marginal totals. Notice they use the word margin because they're in the margins. You see? All right. This is a margin. These are margins and these are margins, right? And this is the grand margin, right? This is the grand total. And notice that the marginal totals, both for the rows and for the columns, equal to the grand total. All right. Marginal. Now, these four boxes, they call them cells. These four cells here represent joint counts, because they are involved with what? With both variables. For example, what's the count for the number of cells that were in North America and not dry?
31,575.
Right. And how many were in South America but were dry?
404.
404. Yeah, those are joint sums because they're occurring with two variables occurring together. Yeah, you see how it works? So these four numbers are joint numbers, and then these two and these two are marginal totals, and this is, of course, your grand total. Now we can use probabilities here, right? So let's see if how good you are. What's the probability that if you picked a well at random, right? What's the estimated probability that the well is from South America? And you don't have to reduce the fractions. Just give me the fraction. So if I picked one of these wells at random, what's the probability that it's from South America?
2,967 over 48,673.
Exactly right. Yes. Because the sample space, remember, is the total denominator, right? And I'm saying, what's the probability of South America? South America is a marginal total. So you look at the margin for it. What's the probability that you picked if you picked a cell at random, that it's not dry?
Could you repeat the question? I didn't catch it.
If you pick a well at one of these gas wells at random, what's the probability that it's not dry?
Oh, 34,138 over 48,673.
Good. If I picked a well at random, what's the probability that it's from North America and it's not dry?
31,575 out of 48,673.
Exactly right. Good. Now I'm going to be a little tricky here. If I pick a dry well at random, what's the probability that it's from North America?
$14,131 out of 14,535.
That's exactly right. Notice what I said. If I picked a dry well at random, so that is a conditional probability. Okay. When I say I picked a dry well at random, that's the knowledge. What I've done now is limited the sample space from 48,673 to 14,535 by saying that. Okay. What if I picked a South America well at random? What's the probability that it's dry?
$404 out of 2,967.
Very good. Very good, Mo. Now, Mo, I expect you get 100 in the next test, all right? All right, you see how it works? These are conditional probabilities. All right? All right, good. So let's get to the next one here. Now, sometimes, again, we use these Venn diagrams to represent our sample space. Now, the sample space here is 48,673 wells, all right? And we're not going to show each of those wells. We're going to just display it as a count, all right? We're not going to list all the wells. So what's listed here are the counts of these. Now the question is, with when you have two variables like this, how can you possibly represent it all inside this box? So what you're going to do is you're going to pick the two variables. All right, you're going to pick the two variables as one variable being one of the circles and the other one being the other circle. Okay. Now, inside the circle for n is how many? What's the total for that? What's inside n here? What's our total? N represents North America, right? The number of wells in North America. What's our total inside this circle? What must it be?
45,706.
Exactly. This is D, the number of dry wells. What's the total for that? What's the total of dry wells? These are marginal totals, right?
404.
No, marginal. Inside this entire D here, what's the total?
14,535.
That's right, it's this number. So inside N is this number. Inside D is this number. What's in the middle here? What's this?
North American wells that are dry.
That's right. That's the joint total of these of N and D. It's the number of wells that are shared in N and are shared in D. Would you agree with that? This total includes the 14,131. This total here includes the 14,131. What's this total? Why is that sitting there? 31,575. Where did they get that from?
It's North American wells that are not included in the dry circle. So it is North American wells that are not dry.
That's right. It's this number here. Doesn't that make sense? There's 14,131 of the North American wells that are dry. That means they're shared between these two sets. And there's 31,575 that are not shared between these two sets. That's the other North America wells. What's this number?
the number of dry wells in South America.
Right. Well, what's in the middle here is the number of dry wells that are in North America. This is the number of dry wells that are not in North. What's the sum of these three numbers mean? If I added these three numbers here, what would I get?
Oh, you would get the number of wells that are either North American or dry or both.
Okay. But you have to be a little more specific about that. Now you could say the number in North America or the number in that are dry. Now, when you said it like the way you said it, you're sort of double counting. So what, to say it your way would be the number of in North America that are not dry, the number in North America that are dry, and a number of that are dry that are in South America. I mean, you see what I'm saying? You have to be a little more specific. But
Yes.
if you simply say it's the union of the number that are in North America and the number that are dry, the union of those, using the addition principle, that would be the sum of these three numbers. And the way to look at it would be, 45,706 plus 14,535 minus 14,131. That would be the sum of these. That's the addition principle, right? The sum of n plus d minus the n and d together is this one. So this plus this, it's this circle plus this circle minus the middle, because this circle includes the middle, this circle includes the middle. So you subtract one of these and you get the sum that you're seeing here. What's this number? This is 2563.
The only one that's not included in the graph, so the dry ones in South America.
I'd say that again. No.
The not dry wells in South America.
Not dry wells in South America. Yeah. So this here represents all the others. It's the complement of both of these together, right? It's not N and not N and not D. They made a mistake here, by the way. Not N and not D should be this here, 2563. They're pointing to the wrong one here. All right. This 404 is not, this 404 represents what? This represents D, not, and not N. This is D and not N. This should be D and not N. This here is not D and not N. This, by the way, is the complement of the union of these three.